operating efficiently. An important aspect of turbine operation is lubrication of the turbine shaft bearings. This is accomplished by the turbine lubricating oil system. Oil is also used to operate valves that are designed to control turbine speed. Turbine speed control is another important aspect of turbine. This illustration shows a typical turbine lube oil system. Its basic components are a reservoir, a main lube oil pump, a booster pump, and one or more oil coolers. The reservoir is the central collecting point for all the oil in the system. In this system, the main lube oil pump is attached to and driven by the turbine shaft. It supplies oil to the turbine control system. The booster pump is powered by the discharge of the main lube oil pump. It supplies oil to the suction of the main lube oil pump and to the turbine bearings. The lube oil coolers are located between the booster pump and the bearings. They are heat exchangers that use a flow of water to cool the oil. The coolers are usually arranged in pairs, with one used for cooling and one remaining ready as a backup. Oil from both the turbine bearings and the turbine control system is returned to the reservoir through return lines. The lube oil system is called a closed system because oil is used over and over again. In addition to the main lube oil pump and the booster pump, a typical turbine lube oil system has 3 other pumps: an AC auxiliary pump, a DC emergency pump, and an AC turning gear pump. The AC auxiliary pump is incorporated into the lubrication system to supply oil during startup and shutdown when turbine shaft speed is too slow for the main oil pump to be effective. It can also be used during emergencies, such as a trip, to supply oil to the turbine when the normal oil supply is interrupted. The DC emergency pump is a battery-operated pump that is designed to supply oil when AC power is not available. It is not intended to circulate oil during continuous operation. It supplies only enough oil to allow the turbine to coast down without damage if all AC power is lost. Following a shutdown, when AC power is available, the turbine is placed on the turning gear and oil is supplied to the turbine bearings by the turning gear pump. Following a shutdown, warping of the shaft will occur unless constant rotation is maintained while the turbine cools down. A warped shaft can result in rubbing between stationary and rotating parts and severely damage the turbine. Even cooling is made possible by the turning gear, and these serious problems are prevented. Another important part of the lube oil system is a vapor extractor. A vapor extractor is a small fan or blower connected to the top of the lube oil reservoir. Oil vapor and other combustible gases tend to accumulate in the reservoir and could cause an explosion if ignited. The vapor extractor draws these gases out of the reservoir and vents them before they can cause serious problems. The pump is not in the standby or automatic position. It will not start automatically when it's needed. If the pumps fail to start, the bearings may not receive lubrication and damage could occur. It's also important to check bearing oil temperatures. This should be done at several locations around the turbine. Readings should be taken at the inlet and the outlet of the cooler to make sure that the cooler is operating properly. Oil temperature readings should also be taken at the supply and return lines. Oil temperature from the cooler to the bearing should be virtually constant. The temperature of return oil will vary depending on load, ambient temperature, and the specific bearing. That the normal temperature of a particular bearing is 150 degrees Fahrenheit. But over a period of 5 or 6 hours, you see the bearing oil temperature rise to 175 degrees. Let's say the maximum temperature limit for the bearing is 180 degrees Fahrenheit. Even though 175 degrees is below the limit, you should suspect that something is wrong. The increase in temperature has been too rapid, and the temperature is well above the normal value. You should inform your supervisor of this problem, and a check of the turbine should be made. Now, on the other hand, let's suppose that the normal temperature of a bearing is 160 degrees Fahrenheit, and over 5 or 6 hours of operation, it varies by a few degrees. Under these circumstances, you can be fairly certain that the bearing is operating normally.